Experiment 2. Hardening by solid solution. Please refer to the practical guide for general comments, rules, and regulations, as well as the criteria required to successfully complete this experiment. All metals have a crystal lattice, which is a highly ordered configuration of atoms that varies depending on the element in question. Common crystal structures that are observed in metals are body-centered cubic, face-centered cubic, and hexagonally close-packed. In order to understand solid solutions, it is necessary to understand binary phase diagrams. A binary phase diagram is a graph that shows the stable phases that exists between two elements across a range of temperature and chemical compositions. In this graph, there are regions where only one phase is stable, and this is known as a single phase region. If we consider the binary phase diagram for aluminium and copper up to 60% copper, the single phase regions are alpha, theta, and liquid. Between these single phase regions, there are areas known as two-phase regions, where two phases are stable at the same time. These regions are the liquid plus alpha, liquid plus theta, and alpha plus theta regions. As we approach the alpha single phase region, the volume fraction of alpha increases. Similarly, as we approach the theta single phase region, the volume fraction of theta increases. An example of a solid solution can be seen when the aluminium-rich alpha phase accommodates copper atoms into its crystal lattice. Considering a substitutional solid solution such as lead and tin, it can be seen that the lead-rich alpha phase can accommodate a maximum of 19.2% tin in its crystal lattice. This occurs at a temperature of 183 degrees Celsius. There are two types of solid solutions: substitutional and interstitial. We will be focusing on substitutional solid solutions. Due to the difference in atomic radii of lead and tin, internal stresses are imposed on the crystal lattice, and this, in turn, increases the alloy's resistance to plastic deformation. There are 4 rules that govern whether or not substitutional solid solutions can be formed between two metals. They are known as the Hume-Rothery rules. They state that for complete solubility, the difference in atomic radius between the solute and solvent atoms must be less than 15%. The metals must have the same crystal structure, the metals must have the same number of valence electrons, and the electronegativity of the metals must not differ by much. This table contains several properties of lead and tin. The objective of this practical is to determine the effect that small additions of tin have on the hardness and density of lead. Please pay close attention to the practical demonstration. You will be provided with both lead and tin. Place a piece of paper on the scale and press the tare button in order to zero the scale. Now, weigh out the correct amount of lead and tin for each sample. Place 2 casting molds next to one another, ensuring that you leave a 5 mm gap into which the molten metal will be poured. Turn on the heating coil and preheat the crucible before firmly tapping it on the metal plate provided, in order to remove impurities that may have built up in it. Now place each combination of lead and tin into a separate crucible and quickly place the crucible back on the heating coil. Once the metal is molten, pour it into the gap between the molds. Give the metal a few seconds to solidify before removing it from the mold. Sand down the rough edges of the casting in order to ensure a smooth surface on which to perform hardness tests. Take note of the load and ball diameter of the Brinell hardness tester. Lift the load and remove the wooden block that it rests on. Place the sample under the steel ball and gently apply the load to the sample. Leave the load on the sample for exactly 30 seconds before removing the load. Place the wooden block under the load when there is no sample under the steel ball. Use an eyepiece to measure the diameter of the indentation.